Yes. In Cal 3, your limits of integration will turn out to be functions, not just variables, like functions. Like you might be doing something like the integral from 0 to 3, and then you'll have another integral from maybe like 0 to x squared minus x, and then an integral maybe from 0 to 2y, and then in here some function, and you're integrating with respect to like x, y, and z, like it's called a triple integral. So your limits of integration can be functions. Yeah. But that's Cal 3. Not to be intimidated by it. I mean, it's just a process. You just have to take your time through it, and it's understand what you're doing.
I have a question.
Yes.
Outside the scope of this, that's fine.
Okay.
If you have data that creates a curve, so you've taken measurements of some kind and you've created a curve.
Okay.
Can you use that to then create a function? Like, is that?
Okay, so this is actually a really good question. Not that any of your other questions have not been good, but this is one that I remember as a student thinking. It's like we study all these functions, right? But in the real world, we have data, right? Or data. Are you a data person or a data person? Data, whatever. Okay, so you've got data, right? We know how to find areas, derivatives, all that, but how do you convert the data into a function? And so that's called regression modeling. So if you have data, you can fit a curve to it, and there's different methods to do it. There's a whole branch of math that's dedicated to that. You asked. I show it's worth everyone seeing this. If you've seen it, great. If you haven't, then something to learn. So I don't know how many of you have any experience with Excel. Excel, no? Yes? I recommend you learn some basic Excel, okay? It's not like super powerful. Well, it is super powerful, but like it's not great for every math-related thing, but it can make life a lot easier with certain things. So, yeah, or Google Sheets, it's free online. Yeah. Okay, so here's what I'm gonna do. Let's get some data. So 1, 2, 3, 1, 2, 3, and then I'm just gonna copy that format. So I'm gonna have 20 data points, and then, should I make these random numbers?
Yeah, do it.
I'm just gonna do random numbers. There we go. And then boom, and then now I'm gonna copy that, and I'm gonna paste it, and so it doesn't change anymore. Every time I hit enter, it'll keep changing. Oops. There. Okay, there we go. So I've got random points. Now what I'm going to do is I'm going to make a like a scatter plot of this. Oh, where's my scatter? Hold on. Hold on. I'm just going to grab this. There we go. So that is a plot of my 20 random points. And then what I can do is just on this chart, I can, hold on, I haven't done this on a while. Where is it? Trend line, there we go, trend line. And you can go and actually tell it. Do you want to fit a line to it? An exponential function? More options, here we go. So here, what I can do is I can say, try and fit a line to this. So it's going to try and fit the best it can a line to the data points. And you can even ask it at the bottom to display the equation. So now, I'm going to go ahead and close this. Now you have it, that is your linear function right there.
Does it get rid of outliers?
It's fitting the best model it can. No, it's not. It's doing what's called like a least squares regression. It's like trying to measure the distance between the line and these points, and it's trying to minimize that distance. So there it is. That's your line, right? Now that's a linear. Now if you wanted to, you could add a trend line. Well, I don't know. What do you want to do? We could do a polynomial, and we could do a higher order. I think it only goes to 4 or 5. There we go. And I can display the equation on the chart. And now I can close that, and now I have a fifth degree polynomial function I have a fifth degree polynomial function that models this data, kinda, not great, but these were random points. I mean, in the real world, you're probably gonna have some trends that are a little better, but so your question is, if you have data in the real world, how do you get to a function, right? So there's a whole branch of math on how you take data and fit certain functions to them. And we do the best we can. I mean, it's not always possible to get a perfect function that's gonna match your data exactly, but you're just trying to like trend. Yeah, that's, okay.
Is this kind of how Leatherman do it?
Well, they have a lot more variables, right? They have a lot of inputs, right? So, okay, yes.
Does that branch of math have a name?
I don't know if there's a technical name for it, but I know that there's people who, it's probably computer programmers that are sitting there, you know, they're mathematicians, computer science programmers, and they're trying to come up with algorithms to best get, and then, you know, they probably classify data into different types of categories, and then, yeah, it's regression modeling, right? So it's, if you want to call it that. Political science, is that what you said?
Yeah.
Oh.
It's a lot of statistics majors.
They're trying to guess who's going to win the election.
So look, I want to go back to something here because I think this is our last little thing we're going to say about this. No. Still no. Okay. So take a look here. What you see on the left is the graph of the function 3x squared. I made it 3x squared because the antiderivative of that's pretty nice, right? What the fundamental theorem of calculus tells us is that if I want the area under this curve, then what I do is I go to the antiderivative of that function. So there's the antiderivative, there's the graph, right? And I need this to be bigger.
I think it's
So-
control.
Yeah, control, mouse
Hold
wheel.
control and squeal. Or scroll.
And squeal. Control and squeal.
I meant to say scroll wheel.
Okay,
but it came out
I got you. So here, where was it? Where'd it go? I lost it. There it is. So there's the graph of 3x squared. If I want the area under that, what I do is I go to the graph of its antiderivative, and I take the height of this endpoint, the height, and I subtract it from the height of that endpoint. And that height difference is the area of that curve, underneath that curve, which is weird, right? I mean, that's weird, but that's the fundamental theorem of calculus. If we do another example, this one, that's 2x, right? If I want the area under that, what I'm going to do is go look at x squared, and I'm going to look at the height difference at the two endpoints. So if I take x squared, there's the graph. The height here is 4, the height here is 0. The difference between those is 4. So that's our area.
So it's just that, like along the y-axis.
Yeah. Yeah, exactly. Well, you need to know the two endpoints where like here I'm going from 0 to 2, right? So what I'm doing on the antiderivative is I'm looking from 0 to 2. I'm looking at the height difference between those 2 points. That's weird, right? Okay. We have 25 minutes. I'm ready to transition into the next idea, all right? So the next idea is improper integrals. Okay, hold, control, and squeal. Oh, that does, yeah, that works. Oh, and it goes in increments of 10. I like that. Learn something every day.
On the keyboard also helps.
Control what?
Plus or minus on the keyboard.
There we go. All right, so improper integrals. So this topic is broken up into two sections, two ideas within a main idea. Everything we're about to study are called improper integrals. There's two types. First type of improper integral is called an improper integral with infinite intervals. That's the first type, and we're going to focus on that completely right now. So everything we've done up to this point, right? You've seen we've been trying to find the area underneath the curve. Here's our function. We start at A, right? We end at B. And and we try and find that area, right? And the fundamental theorem of calculus allows us to do that. But who says the interval has to be finite? What if the interval doesn't go from A to B? What if it continues to go forever in one direction? So what if we have something like this, where maybe you want to start at 1, but you want to go forever, right? Or maybe you have it the other way, where you want to start at forever that way. What's forever that way? Negative infinity. You want to go from negative infinity all the way up to -1, right? Or what if you want to do something like that, where you go in both directions forever, right? Does it still make sense to even talk about an area in this case? Well, you would have to have, your function would have to behave a certain way, right? It would probably have to be asymptotic, meaning that as you move this way, if you want to go that way and actually get a finite number, maybe, that this should tail off to 0, right? It should taper off. Because if it stays up here, shouldn't the area be infinite?
Yeah.
So, but what if it tapers off? You know, is it possible to get a finite answer?
Below the x-axis?
Yeah, what if it goes below and then back up, or below and back up, like a sine function, right? So that's what we want to look at, right? Everyone kind of understand the geometric idea? We want to go like in one direction forever, or the other direction forever, or in both directions forever. Those are called infinite intervals. So let's set up the first problem, and then I'm going to show you how we attack it. So as your first example, let's look at the integral, the definite integral that goes from 1 to infinity, and let's look at 1 over x dx. It's probably worth it for us to know what that graph looks like. So we're starting at 1, right? What do you get when you plug 1 into that? 1. Okay, and as I go to the right, what happens to this function? It starts getting smaller, right? You plug in 2, you get a half. Plug in 3, you get a third. Plug in 10, you get 1/10. Plug in 100, 1/100th. Plug in a billion, 1 over a billion, right? Are you ever going to get to 0?
No, probably not.
Never, right? No matter what x value you ever pick, it's going to be 1 over that x value. Now, it may be infinitesimally small, but it's never 0, right? So what happens is this graph asymptotically approaches 0. And so the question is, if we look at this area under here, is this area finite or not? Do we get a finite area or not? What do you think? What does your instinct tell you? Do you think it's an infinite area? Infinite?
I think it would probably be defined.
It would be what?
Defined?
So you think it's a finite area?
I think so.
We can argue about it, and we can sit here and debate, right? Let's see what the math tells us, okay? Let's see what the math tells us. So how do we do this? First, how do we do this? Well, we're supposed to find the antiderivative, right? Fundamental theorem, and then plug in the two endpoints. But see, there's a problem. We're plugging in infinity. And infinity is an idea, right? It's not a number. So what we do instead is this. We're going to do a limit. We're going to rewrite this integral and act like it's going from 1 to, let's say, t. You can use any variable you want here. Just don't use x, because you're already using x inside here. And then what I want is to see what happens when I let that t go to infinity. So does that make sense that I'm going to rewrite it this way? I'm replacing infinity with t. I'm going to figure out what happens, right? Because if I take this out, do you all agree that that answer would give me the area all the way out to t, right? Yeah. And then what I'm going to do is I'm going to let t take off to infinity. So I'm going to try and come up with a formula that tells me the area up to t, and then let that t go off to infinity and see what happens to the formula. What is the antiderivative? Keep this limit out front. Keep this limit out front right now. Oh, well. What is the antiderivative of 1 over x? Natural log of the absolute value of x, right? And then I want to evaluate that from 1 to t. So I'm gonna put a set of brackets around this. You don't need to do this, but I just want to stress that the limit is going to come, okay? It's not yet, though. Okay, I'm just doing This limit is sitting out here. I'm going to do the limit, but not yet. First, I'm just doing the antiderivative. Yes?
As a quick question, so I think we went back to Cal 1, the limit when talking about the natural log of x.
Mhm.
Didn't the left and right hand limits disagree with that?
Did they what?
The left and right hand, the left and right hand limits disagree, or was that only in the context when it approached 0?
Only when it approaches 0, I think, is what. Because the natural log function is not defined for negatives. I'm not sure we're talking about the same thing right now. But we're going to infinity, so we're not talking about what's happening at 0. Let's keep going and let's see if we run into what you're asking. Do we need the absolute value?
No.
Generally, yes. When we take an antiderivative of 1 over x, we need the natural log of absolute value of x. But what are the things we're plugging into this? They're all positive numbers, right? Because I'm going from 1 to infinity, so I'm only dealing with positives. So I don't need the absolute value anymore. T goes to infinity. Okay, now let's do this. I'm going to plug in two things, right? So I plug t in for x, right? So I'm not going to do the absolute value anymore. And I plug in 1. Now, of those two, one of those you should know. The natural log of 1 is 0. That's kind of like one of those things you should know. The natural log of 1 is 0. A calculator could verify that. And so really, all we have is this. What is the limit as t goes to infinity of the natural log of t? Right? That's all we have left. And so what this is asking you is to consider, what does the natural log function do as its argument goes and gets bigger and bigger and bigger? It goes to infinity. You can verify that by thinking about what the natural log function looks like. This is what natural log of x looks like, right? It looks like this.
Yeah.
So if I'm letting t go to infinity, I'm basically letting that go to infinity. And as you go out this way to infinity, what happens to it? It gets bigger, right? Not real fast, but it does get bigger, right? So the bigger x gets, the bigger the natural log function grows. And so it will head to infinity as well.
Yeah, so I guess that's what I was asking, was I was saying something like these behave similar to limits in Cal 1.
Oh yeah, we're going to do a lot of Cal 1 limits right now. Well, we only have 15 minutes left, but yes, we're going to be going back to Cal 1 and doing limits, L'Hopital's rule, things like that are going to come in. Yes?
So if the antiderivative of a function would have an asymptote, because this, it kind of, it looks like an asymptote, but it's not. It goes.
Yeah, you have to know that this is not an asymptote, yeah.
So if our antiderivative of our function did produce an asymptote, then our area under the curve would be defined?
Mm-hmm. Absolutely. So what we've determined from this answer, infinity, is that if you try and take the area underneath this curve from 1 to the right forever, that we're not getting a finite number, that it's getting bigger and bigger and bigger. The area is becoming infinite. So what we say right now is we don't say that the answer is infinity. What we say is that this integral diverges. And we're done. These notes will be formal. I'll bring up the notes and I'll explain this. If you get something over here that is not a finite number, like if you do this and you get the number 4, then we will say it converges. But if you get something other than a finite number, like infinity, or maybe the limit doesn't exist, then you will say that the integral diverges. Let's try another one. Okay, I'm going to make a slight tweak to it. I want us to do the area underneath from 1 to infinity of 1 over x squared this time. That's almost the same function. If you graph it, plug in 1, you get 1. As you go to the right, it drops again, doesn't it? It just drops faster, right? So it drops down. And we want to know the area under that, right?
So without even doing it, you could basically assume they came the same now.
Well, you would think they did, right? Because they're both having the same sort of,
It's going negative though.
what's that?
You're going to go negative to get your antiderivative, right?
Well, our antiderivative is going to be different, isn't it? It's not going to be a natural log.
Negative 1 x.
Yeah, so what's going to happen to that? Well, let's do it, let's do it.
Yeah.
We're not get, so this is the actual part I think you're picking up on, is that our intuition is like, this should do the same thing 1 over x did, right? Because, yeah, the areas are getting smaller, but there's an infinite amount of them, so it's going to become infinitely big at some point, right? But the thing is, this is dropping fast enough where it's not, it's, yeah, well, we're going to see it's not, we're going to get a finite number, yes.
I'm still trying to wrap my head around why we substituted in C instead of, I'm sorry, T instead of using X.
T.
Because you're using
Well, we found the antiderivative, right? Let's say that this right here, let's say I'd asked you to go to 4 here. Then this would have been 4, right?
Sure.
And then you put 4 in here, yes? I'm doing the same thing, except I'm plugging in t. And then at the end, I'm letting t go to infinity. Is that okay? You sure? That seemed like an agreeable okay.
I can ask about it after class.
Okay. Let's do this next one and see if it clears up at all. So I want to go from 1 to infinity, a 1 over x squared. So first thing I'm going to do is I'm going to replace the infinity. I'm replacing infinity with t. Replacing infinity with t. And then I'm going to find the antiderivative of that. Okay, you need to find the antiderivative of that. Yeah, that's the same as x to the negative 2, right? That's what that is. Find the antiderivative, so you add 1 to the power, and then you have to scale. So this should, I'm trusting you could do this. Negative x to the negative 1 is the antiderivative of that. But you have to still evaluate that using fundamental theorem calculus. 1 and then t, right? 1 and t there. And I'm almost ready to plug in, but that's, I don't like looking at that. That's kind of confusing to look at, so I'm going to write it this way. All I did was rewrote this by dropping the x down and leaving a negative 1 up top. Almost ready for the limit. So let's see. I'll put this in brackets so you can separate it. Let's see, I'm doing that. I'm not bringing the limit in yet, right? Limit's going to come in at the very end. So I'm doing the antiderivative of this. Or I did the antiderivative, now I need to plug in my 2 endpoints. So first I plug in t for x, negative 1 over t. Then I subtract from that what I get when I plug in 1 for x. See, that's our fundamental theorem of calculus. Plugging in this number here, this number in here. Now, what does this become?
Negative 1.
It's negative 1, so that's a plus 1 at the end, right? But you still have to figure this out, right? That. What's the limit as t goes to infinity of that piece right there, negative 1 over t? That's 0, right? Because what's happening here, your numerator is a fixed number, your denominator gets huge, that ratio gets small, right? And so this heads to 0. So that means this thing heads to 0, and so your answer is 1. So that area converges to, that integral, okay, converges to 1. So we would say for this answer, converges to 1. So if we were to do this, let's say we were to go out and actually don't go to infinity, let's say we went to 100, then we could compute this, couldn't we? And that would be a finite area. Here's what I could tell you. Your answer would be smaller than 1, just a little bit smaller than 1. The further you go out, the closer you get to 1. So maybe if you go to here, you get 0.9. And if you go further, maybe you get like 0.9876. If you go further, maybe you get 0.999742. if you could go forever, you would go to 1. Like the further you go, the closer you get to 1.
And the logs are just
For that function.
Yeah.
For that function specifically. So there's a problem I like to talk about in classes like this where, you know, we had two functions that essentially looked the same, right? They both did the same, but one of them we got divergence, the other one we got convergence. So there's kind of like this classic problem that, if I've shared this with you before in Cal 1, then you've got a preview of this, but it's this idea that if you take a cup, right, and this is purely a theoretical question, we're not going to talk about atoms and things like that and evaporation, and just purely theoretical. Let's say I have this perfect cup and it holds 1 cup, all right? 1 cup. That's all it holds, all right? So now what I'm going to do is I'm going to come in here with a pitcher of water. And I'm going to start pouring water into this thing, all right? And what I do first is I do 1/10 of a cup. And I pour it in there, right? So we have 1/10 of a cup of water in there, right? And then what I do after I've done that, I add to that, now I do 1/100th of a cup in there. So that's less water, right? But I'm going to pour it in there. And now the water level has come up, right? A little bit?
So the limit is 1.
Well, now I keep doing this, right? 1/1000. Pour it. Does the water level come up?
You can't go over 1 cup, basically.
Can I not go over 1?
Not that cup.
Why?
Because it won't hold it. Yeah.
So this is counterintuitive, right? Every time I'm pouring in, right, is the water level coming up?
Yes.
Yes?
Yes.
Okay. So if I did this forever, the next one would be 1/10,000. Next one would be 1/1,000,000. Right? I think I got that right. No, too many. Sorry. I forgot 100,000. You get the idea, right? So what would happen if I did this forever? Would it overfill? Would the cup overfill or not? So this is usually where we take a vote and we say who thinks it will overfill eventually versus those who don't.
I'm gonna say if you had to like human time.
Yeah, like if you could go forever, does it overfill?
No.
Yes, no. So we're seeing a lot of no's, lots of yeses, right? So I think you could make good arguments either way. I think you could make good arguments. As long as we're not talking about evaporation and molecules and atoms, purely theoretical. And the problem with this is if you think that it doesn't overfill, right, which a lot of you say it doesn't overfill, then you have to try and convince me why it is that if you take a positive number and you add another positive number and you add another positive number, because these are all positive numbers, how is it possible to keep adding something each time, add something, the water level's going to come up every single time, and if I do that forever, eventually it will overfill?
Yes, it's because that's not just any random positive numbers you're adding. You have to add some that go with the function. So because you're adding numbers that,
This is a positive number, yes?
yes.
So does the water level come up?
But you can't just.
Hold on, answer my question. Does the water level come up?
Yes.
Does it come up more?
Yes.
More?
Yes.
I'm gonna do this forever.
Yes.
Convince me it doesn't overfill.
Well, I mean, you can't just throw a 5 in there and add a 5 randomly.
I'm not. These are all getting smaller, right?
That's what I mean.
But they're all positive numbers.
They have to get smaller.
But they're all positive.
They have to get smaller.
They are getting, yes, I agree they have to get smaller, but I can tell, well, I don't want to give away the answer yet. I'm not convinced with your argument.
I feel like you have to change the function that we're basing this on before you can make it overfill.
If you change that
Okay,
to decimals,
so hold on, I see a couple hands. What do you think? Does it overfill or not?
No, it wouldn't overfill, and it's because you have to consider it. There's, like you said, it's unintuitive because some, like with a different function it would, and with a different one it wouldn't, and both those functions can look very similar. But there's something very fundamental about certain functions where each time that you fill it, you fill it with such a little amount which is very, very important that it matters in determining whether it would overflow or not.
So what I'm trying to do is find somebody who's going to counter my claim. My claim is that I keep adding positive numbers together and that the water level is, do you agree the water level keeps coming up every time I add a positive number? Yes? Convince me it won't overfill then. If the water level keeps coming up forever, like it keeps coming up, and that's going to happen forever, convince me it doesn't overfill. Nobody has done that. Everyone's saying, abstract, hold on, go ahead.
I think it is going to overfill, but I guess I can try it. I think the reason why it probably won't, if I'm on that side, is because the more you're adding, the longer you're adding it, the smaller and smaller and smaller and smaller to like a molecular level.
Ah! You can't use molecular. This is purely theoretical. Okay? Purely theoretical. And you're also actually supporting my argument because do you all agree that each of these numbers is positive?
Yes.
Yes. So it's something.
That's why
It's something, right?
that's why
I want to hear from someone who doesn't respond. Anyone else who doesn't normally respond have an argument?
Vlad actually has the answer, he's afraid to say it.
Yeah, well, I mean, we can get to the answer.
Isn't it negligible at some point? So you like ask them
These are negligible, right? These are like negligible, but it's something, right? I'm thinking it in the sense of water level, right? Like if I pour something, if something's going in, the water level's coming up. You can't tell me that I pour something in and the water level stays the same, right? Right? So it's more of like an asymptotic approaching of something. So let's answer the question because I'm almost out of time, right? It's a very simple question to answer. We can resolve it right now. Okay, all you have to do is convert these to decimals. So this is 0.1. The next one, 1 over 100 is 0.01. The next one is 0.001. The next one's 0.0001. And if you do that forever, start adding these together. These two together is what? 0.11. And then if you do that one, you get 0.111. And then that one, you get 0.1111. And if you put them all together, you actually get 0.111 forever, which turns out to be exactly the fraction 1/9. So if you go into your calculator and do 1 divided by 9, you'll get 0.111 forever. Which means that if I did this, not only would it not overfill, it wouldn't even fill up halfway. It wouldn't even fill up 1/9 of the way. It would just asymptotically approach 1/9, but never get to it. Right? That's counterintuitive. That's counterintuitive. But this doesn't always, how this actually decreases, how fast these get small matters. Because if I do something like this, is that going to overfill? Are these getting smaller? Yes? Are they getting negligible? Yes? This one overfills. This will overfill.